Hey folks, welcome to Chapter 4, Module 4. We're looking at molecular geometry, polarity, and intermolecular forces of attraction. This is only 3 sections. Each of these 3 sections is in the name of the chapter. So this first section is about the three-dimensional shapes of molecules. And right here on my first page is a picture of molecular modeling kit, which are really useful and helpful in thinking about these structures, seeing them, like holding it in your hand and manipulating it. So if you want to get a model kit, if you want to borrow one, let me know. We have some in our lab spaces. And also, you can find websites and simulations that show you these three-dimensional structures, and you can turn them around on the screen and things like that. So first off, we've been representing molecules basically on a two-dimensional plane, right? On a piece of paper or a screen, like a Lewis structure right here. So this shows simply how atoms are arranged and bonded to each other. But molecules are not flat. They actually have extension in space. And so from the Lewis structure, we can uh, expand it into something like this where we see a three-dimensional shape. And so here is the same ethanol, which is funny, it says drinking alcohol. Methanol, by the way, is not drinking alcohol. You should not ever drink that. You will literally go blind. But ethanol is okay. So this is the flat structure of the Lewis, and in reality, it has this shape here, and is represented by like ball and stick model. That's what we call it, and you can see why. In this, there's a standard. Usually carbon is black, hydrogen is white, and oxygen is red. And so we can see, even though we don't have the symbols here, you can tell what they are if you've seen some of these and you have a legend down like this. There's also the space filling model. That can be a bit hard to make sense of sometimes. I think the ball and stick model is really good. Over here on the left shows that we can actually take the Lewis structures with just lines, and if we add dashes and wedges and be a little bit clever in how we draw it, you can simulate dimension on here, right? So this is CH4, the molecular formula, the Lewis structure, and then now 3 dimensions. So it looks like these are lined up in a plane, and then this one's coming at us, and then the dash is going back into the page. And here's an attempt at drawing that in 3 dimensions. So knowing the three-dimensional shape of a molecule is important, right? It influences how it interacts with other molecules. If we're talking about like drugs or hormones, the shape influences how they interact with their active site or the enzyme they're trying to interact with. And things that have the same shape can compete and inhibit each other. And so shape really does matter. And from the Lewis dot structure is where we'll start. Actually, you know what? I'd even go one prior to this. We have the molecular formula. So from the molecular formula, we learned how to draw Lewis structures. From Lewis structures, we can determine the electron geometry. And then from the electron geometry, we can determine the molecular shape. What these are, electron geometry means the relative positions of the groups of electrons on the central atom. Sometimes these will also be called domains. Okay, and then the molecular geometry is just the atoms, the relative position of the atoms in a molecule. So sometimes there will be groups of electrons, and they won't all be bonding. You can have lone pairs, things like that. So what we mean by group or domain would be any one of the following. Here, it could be a single bond. even a double or triple bond. So a double bond, right, is two pairs of electrons, but if they're kind of in the same area, the same domain, we call it the same group of electrons. And importantly, a non-bonding pair also counts as a group of electrons. So this is important then because we have a theory, which again is a model or explanation of why things are the way they are. And this is called valence shell electron pair repulsion. We call it Vesper for short, even though the S and the P are swapped. Anyway, it's Vesper, okay? We call it Vesper theory. And remember that electrons are all negatively charged, right? And so things that are like charges repel each other. And so these are actually out in space, like around the atom, right? And so groups of electrons on the central atom repel each other to be oriented as far apart from one another as possible. Okay, so groups or pairs, groups of electrons, whether that be a single bond, double bond, lone pair, they want to spread out in space as far away from each other as possible. So when that happens, we get some very predictable shapes. And here they are, again, in 3 dimensions here. We tried to represent this. So on the left, we're going to fill in the number of groups of electrons. And on the right, we're going to name this shape. Okay, so here we have a central atom. And how many groups or domains of electrons are on it? Well, there's one here and one here, right? So there's two. And this shape is quite simply linear. Right? The three atoms, the three, like if this is a group and a group, are separated out from each other 180 degrees in a straight line. The next case, we have a central atom, right, with three electron groups or domains around it. And this shape is just called trigonal planar. And the planar part is important. It means that they're all in the same line. If you set it down on a table, everything would be flat, right? That if you have three groups of anything around a central space, the way that they spread themselves out the most is to be in a flat plane, spread out like this. Okay, in the third case has four, right? 1, 2, 3, and 4 electron groups. And this shape is called tetrahedral, where these would each be oriented towards like a different corner of a box. Okay, and so here is the same information in another way. And again, looking at the sequence, if we have the molecular formula, then we can get the Lewis dot structure. Then from that, we can get the electron geometry. And then coming up next, we'll get molecular shape. So from the Lewis dot structure, we can see how many groups of electrons are on the central atom, right? Again, that's bonding locations and non-bonding pairs summed up together. And if there are 4 groups of electrons, then we get a tetrahedral shape. If there are 3 groups of electrons, we get trigonal planar. And if there are 2 groups of electrons, it must be linear. Okay, that's the type of electron geometry. Now, from electron geometry, what we really want, if we talk about shape of the molecule, is molecular geometry. Because the electrons influence the shape, but they're not actually a part of the shape themselves. Right? You can't really see them. They're very small. So here's a couple ideas. If all the electron groups are bonding groups, then the molecular geometry is the same as the electron geometry. So if there are 4 electron groups and all 4 are bonds, then the shape is tetrahedral. But if one or more of the electron groups are non-bonding electrons, then the molecular geometry is different from the electron geometry. The molecular geometry is different from the electron geometry. So in part 2, we are going to go through all of the possible combinations of electron geometries and molecular geometries.